You at the end
Okay,
of the Zoom. Okay, all right.
you good to start?
Yes, in that case, I guess I'll start. Hello, welcome everyone for coming to PhySU's first ever colloquium. This will be a series that will go throughout the semester. I will try and have it more or less regularly, so please do follow us on Discord and Instagram so I can hear more about what we're planning, and of course other events like social events and academic events, so on and so forth. Today, for you, we have our speaker is Adi. He is a fourth-year undergraduate pursuing an astronomy and physics specialist with minors in chemistry and math. And he's also the vice president of PhySU for communications, if you don't know him already. He works with astronomical instrumentation at the Dunlap Institute for Astronomy and Astrophysics at U of T. His research projects involve characterizing sCMOS detectors for optical astronomy with Prof. Ting Li, and designing an RFI mitigation system for radio astronomy with Prof. Juan Mena Parra. So everyone, please welcome Adi.
Thanks for the intro, Ivan. So hey everyone, as Ivan introduced, I'm Adi, and today I'll be talking about my research with the CMOS detectors and why they might potentially change the way optical astronomy imaging happens and has been happening for the past 50 years. Before we get into it, I want to talk a bit about the background and history of optical astronomy and imaging to see how we got where we are today. So let's start way back, right at the start with the naked eye. For most of human history, this is what astronomy imaging was. You look up at the stars, and then as best as possible, you try to draw out the stars that you see on a piece of clay tablet, parchment, or whatever the writing tool of your time was. As you might expect, these recreations were really crude and dependent greatly on the astronomer's eyesight, memory, and artistic skill. The first image on the screen is an ancient Chinese star map from AD 700. As you can see, it's not very detailed, and it's mostly comprises only of constellations. Bonus points for anyone who can find the Big Dipper on there. And of course, despite being limited to just the naked eye, the ancients weren't without their own fancy tools to make it easier for themselves. So one of the types of tools they used was something called an astrolabe, like in the second picture here, which was invented in around 100 to 200 AD. And it kind of helped measure the position of stars or measure the altitude of stars. And it also helped locate stars. And so it was used for things like naval navigation up until the 17th century. Although despite these tools, the resolving power of astronomy was still limited by the human eye, which is about 1 arc minute, which is 1/60th of a degree. And for like a sense of scale, a full moon in a bright sky, in a night sky, is on average 30 arc minutes. So really small. The first big technological shift in optical astronomy, of course, came with the telescopes, which were invented in 1609, but not for astronomy, until Galileo designed a new type of telescope in 1610 for astronomy purposes specifically. They allowed humans to see further into space and resolve details that the unaided human eye never could. But astronomers, being astronomers, weren't really satisfied with Galileo's design because it only provided an angular magnification of like ×3. So just the next year in 1611, Kepler designed his own telescope, which was still a refracting telescope that uses lenses. And this telescope could provide a much greater resolving power, but because it uses lenses, you needed to have like a ridiculously long tube, like in that second image, to get like a good power. To get good resolution. This issue was mostly solved by Newton, who invented the reflecting telescope that uses a set of mirrors that allowed us to build powerful telescopes that were still in manageable sizes. You'll notice, however, that we are still in the age of looking up at the stars and then trying to draw what we see on paper until about 1840. When photographic plates were first used for astronomical purposes. And now finally, we were able to capture the night sky as it was permanently on like a physical medium. And the ability to permanently and accurately record the night sky essentially revolutionized the way we did science with astronomical data, because it allowed us to track the time evolution of bodies and see how they moved about in the sky. In fact, these two images show like two of the greatest, well, arguably greatest things that photographic plates were used for. So the first image there shows an image of Andromeda as taken by Edwin Hubble. At this point, we didn't know galaxies existed. And so Andromeda was thought to just be like a big nebula or a cluster of stars in the Milky Way. But also we didn't know Milky Way was a thing. So using this image, and once taken like a couple days before and after, Hubble was actually able to identify this star, which he labeled as bar, as being a Cepheid variable, which oscillates in brightness regularly. And he was only able to do this by comparing photographic plates from different days and seeing the star get dimmer and brighter on the different plates. And using this, he was able to kind of figure out that the Andromeda was much further away than most other things. And this eventually helped lead to the realization that it's a distant galaxy. The second photo shows the discovery of Pluto, as these photos taken like 6 days apart show Pluto moving in its orbit from here, or roughly here to here. And because of how small Pluto is and how dim it is, if we didn't have a way to permanently capture the night sky, this probably would not have been possible with just the naked eye, and what might have been marked off as just like human error. Okay, finally, we entered the digital age with CCDs in the 1970s. The first photo of the night sky with the CCD was taken in 1976, and it gave us quantitative data to work with. So instead of just looking at the night sky or having pictures of the night sky, we were actually able to associate numbers with each pixel that gave us a clue of how bright or dim objects were. This led to an explosion of the types of sciences that we could do in astronomy. And we still use CCDs in optical astronomy now 50 years later, although the CCDs used now are obviously not the same as their ancestors. Apart from just being able to quantitatively analyze these images, CCDs gave a much higher sensitivity to light compared to photographic plates. They had better responsivity to a broader range of wavelengths. They were immediately viewable and didn't need to be developed. And they had a linear relationship between the exposure time and the light gathering capacity, which, as I'll explain later, is really important. Also, they gave us the ability to use software to do things like noise subtraction, correct for bad pixels, etc. Okay, so what comes next? CCDs were invented in 1976. We still use them in 2024, but all technology has to change at some point. And so what comes next? And why do we want to move away from CCDs, given that they are able to take such high quality data? These are some of the questions I'm trying to answer, and I'm trying to propose the CMOS as a potential replacement for the CCDs. So what is a CMOS or an sCMOS? A CMOS is a complementary metal oxide semiconductor, with sCMOS simply being the scientific grade CMOS. Much like CCDs, CMOS chips are silicon-based and contain photodiodes that are able to translate the incident photons into electrons via the photoelectric effect. And then each pixel is able to accumulate charges based on how many photons it encounters. And then once you read out the data or take an image, these accumulated charges are turned into voltage signals that are eventually converted into digital units that you see on your computer. In my project, we're only concerned with something called a backside illuminated CMOS or sCMOS, which just means that all of the metal wiring is below the photodiode instead of above it. And this helps a lot with noise reduction and is a technology that has only been recently possible because initially sCMOS or CMOS had the metal wiring in front. So what is the difference between CCDs and CMOSs? Well, the CCD essentially acts as one big detector and is read off row by row. So each pixel kind of gets read into the horizontal shift register, which then amplifies and outputs the voltage. And then each preceding pixel shifts onto the empty pixel. But in the case of a CMOS, each pixel is essentially its own detector because it has its own independent amplifier and circuitry to perform the voltage conversion. And the method of the readout is really what causes significant differences between the quality of images, amount of noise, and general properties of CMOS and CCDs. A much easier way to understand this is using something called the bucket analogy. So let's think of photons as being raindrops. And instead of using a camera trying to capture light, you lay out a bucket of grids on the ground while it's raining. And you essentially want to measure how much rain there is in each area. So you want to measure the amount of water in each bucket. In the case of a CCD, this is essentially, okay, this is the only spot where you're allowed to make measurements. So in the case of the CCD, you would take all the buckets in the front column, measure them, move all the water from the next bucket over to the first one, the third for the second, and so on, until you've read out each column of buckets one by one. In a CMOS, on the other hand, the entire region of the detector is you're able to take measurements. So you can go and measure all of the buckets at the same time. You can measure only a subset of the buckets. You don't have to worry about all the water being transferred from bucket to bucket like you do with the CCD. Okay, but why change from the CCD? Because the CCD is not a perfect technology. Because the readout method of transferring charge from line to line results in a lot of image artifacts that can ruin your data. One example of this is the blooming and smearing, which is when a pixel saturates and the charge kind of leaks into the neighboring pixels. This is the same as if your bucket was full of water and then it started to overflow into the neighboring buckets. And because it has a line-by-line readout, it's easier for the charges to move along lines. Like it's easier for the charges to leak in one direction than the other, which is why you see the vertical lines that are called smearing. The second kind of image artifact you can get is that if you have a single bad pixel, that essentially ruins your entire column of pixels because you can no longer transfer the charge from all the pixels behind it. And that leads to bad columns like these or like partially bad columns like this, where this region is read out just fine, but this entire region is lost. Yeah.
So the image is being read like this.
In this case, yeah, the image would be read like row by row.
Also, it's like this.
Yeah, so it's being read like this, so all of the data is being transferred like this, which is why with the one bad pixel, you see a loss in data above it. Right. Since the CMOS doesn't have to worry about this line-by-line read, we don't really see these with the CMOS. Okay, so now that we know what a CMOS detector is and how it differs from a CCD, why do we care about it? Well, the CMOS detectors were invented at around the same time as the CCDs, but basically underperformed in every single metric. They produced lower quality images, had lower sensitivities, higher total noise, a nonlinear relationship between exposure time and light detected. And all of these reasons made it so that astronomy ended up adopting CCDs for scientific use. However, these downsides don't really matter too much when you're, say, taking a photo with your phone, because you have a lot of light. And so the noise and loss of data resulted by the CCD is effectively drowned out by all your signal. And because of this, CMOS saw widespread use in consumer electronics, like your phones, your webcams, or your professional cameras. And because of this widespread consumer market that CMOS has had, manufacturers spend like a ton of time and money researching and developing CMOS technology, to the point where we now have something called the sCMOS, or the scientific grade CMOS. Right, so these scientific grade CMOS are able to give us performances that are on par with or even better than the scientific CCDs, and also offer advantages like they being cost effective, having faster frame rates, lower read noise, and lower power consumption. And these scientific CMOSs were invented in 2009. But why has it taken us over almost 15 years to start thinking about their use for science cases? Well, it's to do with the loop of consumer use to industry focus to increasing performances. So it took a while for the CMOS to really reach a point where we can actually start to consider them for science. And a secondary result of this industry focus on CMOS production is that the industry now no longer wants to produce CCDs because there's just no market for it. And astronomers and scientists just don't form a big enough share of the market to actually be able to justify spending all that money producing CCDs. And in fact, Sony and On Semiconductor, which are two of the biggest producers of semiconductors and CCDs, are both discontinuing their CCD production and sales and support. So as you can see, On Semiconductor already ended it 4 years ago, and Sony will end it within the next 2 years. So if we want to keep astronomy or scientific astronomy cheap, or relatively cheap and relatively easy to find instruments for, it is really important that we start looking and characterizing these sCMOS detectors. Okay, I'll take a short question break. Yeah.
So, like, what exactly do they have to change about the, like, what is exactly like the main difference between like CCD and CMOS? Is that made for its like higher readings? Is it just because like we had all like needed like ICs and like products it's like each of the different or it's something else that like kind of forced to like fixes it smaller or something like that?
I'm not totally sure what exactly about a CCD gives it a higher read noise than a CMOS. I could look into it later, but yeah.
It could be because like, say on higher pixels in the column, you have a lot of norms that's like, like water, like with a bucket analogy, water.
That's possible. Maybe. Yeah. So essentially what read noise is it is like unavoidable noise that is being generated whenever you like read a signal. So there's no way to absolutely eliminate read noise, but somehow CMOS have managed to reduce the amount of signal generated when they read out the data. Yeah.
So based on the analogy, were you saying that if the pixel on the CMOS was read and exported individually rather than by column?
Mm-hmm.
So that means with CCP, you will basically stack the read points to take data on columns, where CMOS the reading ones are like not stacked.
that could be it. Again, I don't really know. So all of your suggestions might be true, might not. I don't know, but I can definitely look it up later. Yeah. The what, sorry? Oh, it's because,
Repeat the questions just so that people.
right. So Addie's question was, how does CMOS get rid of the blooming and smearing effect? So the blooming and smearing is caused due to the line by line read. So because the CCDs have like a line by line readout, it's a lot easier for the charges to move in one direction compared to the other, which is why you only see the smearing in like, you only see vertical lines, you don't see horizontal lines. So since CMOS doesn't have that connection between the pixels, it's not as easy for the charges to flow. And so you don't have like these smears. Yeah.
So you mentioned how the NAP are going to like stop producing CCDs around 2016, so it's been like a while ago. Do you know if there's like a lot of research groups that started looking into it, or like is it something that's like not really being looked into?
Like looked into what?
Like in theory, like is it like on another stage?
So it is being looked at by several groups, although I don't think it's fair to say that it's a common problem yet. Because there definitely are groups that are looking into it, because the reference papers I'm using for my research have used CMOS and have characterized them. And there's just a lot of sCMOS out there, so I'm sure it is becoming increasingly common. But if it is very common, is hard to say. But it's like a problem that everyone is aware of. Yeah.
What's the actual?
Oh, it's a silicon semiconductor. I think I had a picture here. Right there. Well, I guess it doesn't say what it's made of, but they're silicon based. Okay, I'll move on to the actual research part. Okay, so this is a list of 5 detectors that we chose to characterize for this research. As you can see, they have like varying pixel sizes, because different pixel sizes have different uses in optical astronomy. So if we wanted to get like a broad sense of range of where this technology is at. Also, some of our selection criteria were that these detectors had to be better, at least in the reported manufacturer values, than the detectors used in our reference papers. And we also had a budget of around 40 to 50,000. So these are all detectors, 40 to 80,000, sorry. So these are all detectors that fit within that budget. Yeah.
So what kind of problem would the detector you were working with be good for in astronomy?
Well, so I was working with all of these over the summer. So it's like there are certain science cases where you want a more broad field of view. You want to look at like a bigger portion of the sky, versus some astronomy cases where you want to really focus in on a small portion of the sky. So that's where like the different pixel sizes and fields of view come in. So yeah, based on these manufacturer reported values, the Hamamatsu Orca Quest was like our front runner. But like we can't just trust what the companies tell us, so we had to characterize all of these values for ourselves. Oh, I will say that I also looked up the specifications of CCDs sold by these same companies. And they stated a comparable linearity here. So the CCDs had around 99% as well. They had higher levels of read noise right here. So the CCDs had 5 electrons, as opposed to all of these, which have less than 2 electrons, which is as expected. But the CCDs did have much lower dark current values, which is here. And it was lower by a couple order of magnitudes. However, the CCD dark current values were also reported at a much lower temperature than the CMOS values, and dark current is really dependent on temperature, as I will talk about now. So dark current, it refers to the spontaneously generated electrical current due to electrons getting excited by the thermal energy given off by your camera itself, which is why the cooler your camera, the lower your dark current, because the lower the thermal energy. It is typically measured in units of electrons per pixel per second. The plots here have units of ADUs per second, which is just like the digital units. And these will later be converted into appropriate units using a conversion gain, which I will also get to later. So as you can notice for these plots, which are for the Andor 11 and Ximea cameras, the dark current does get lower with temperature. You can see like the difference between 10 degrees and negative 25 degrees. But it's really hard to compare the two cameras right now because without them being in like electrons per pixel per second, it's not really an apples to apple comparison, since the conversion from analog to digital units to electron units is different from each camera. Okay, so the next is read noise, which, as I mentioned earlier, is the noise accumulated during the process of the reading of the data and the conversion to digital units. So a lower read noise essentially results in a better quality image because read noise forms the noise floor of all of your signals. So no matter how perfect the conditions are that you take an image in, you will always have at least as much noise as the read noise. Shown here are two 2D histograms. So the smaller one is from my reference paper and the larger one is one I made myself. And the one for the reference paper shows a comparison in the spread of the read noise, the mean signal, and the standard deviation between the signals for a CCD, which is the blob on the right, and a CMOS, which is the big spread on the left. Interestingly, we do not see that big spread with our data. Just for a comparison, their units go up to 40 AUs, while ours only go up to like 10 to 15 AUs. So our data is actually much more similar in dimension to the CCD data, since this is also around 10 AUs. A possible reason for this is because our detectors are of much high quality than theirs were. But just to make sure that it is a fair comparison and that I'm doing things right, we will also be getting like the CMOS that they used and replicating all of their tests to see if I get the same results. Okay, next is a test called salt and pepper identification, which is basically just a way to check which are the good pixels or the normal pixels in your detector and which are the faulty pixels. And the salt and pepper pixels, they just degrade the overall image quality during randomly occurring bright and dim spots, and are they're a result of manufacturing defects rather than like a problem with the technology of CMOS or CCD itself. So there are 4 types of pixels that we're trying to differentiate between with this test. The first one is a normal pixel, which has your average signal and a low standard deviation, such as the blue dots here. Then you have your high pixels, which have a higher than average median and a low standard deviation, so they appear consistently brighter in every image. Then you have your salts, which also have a higher than average median, but a high standard deviation. So the red dots you see here, which basically means that in your images, that pixel would fluctuate a lot, but it will generally appear brighter than the rest of the images, rest of the signals. And finally, we have the pepper pixels, which have a lower than normal median, but a high standard deviation. So they also fluctuate a lot, but on average, they look a lot dimmer than a normal pixel would. So it's important to identify the pixels that are not normal so that when we do on-sky testing, we can take into account the areas in the images where it's like the image is distorted because it's either too bright or too dim, and it's because of manufacturing defects. Then comes linearity, which I've been kind of hinting at throughout. It is a measure of the linear correlation between the output signal generated by the camera or by each pixel and the incident light that each pixel actually gets, with the expectation being that an increase in the amount of incoming photons would lead to a proportional increase in the outputted signal. This is a crucial test for like reliable photometric measurements, because it's basically like if you're looking at two stars and one of them looks brighter in your image, you essentially want it to be that the one that looks brighter in your image is actually brighter in real life as well, and it's proportionally brighter. So yeah, based on just the visual analysis of these two plots for two of the cameras, the linearity is pretty good. It's like above 99.5%. And a final test that I'm doing is called the photon transfer curve, which is a way of quantifying the different contributions of the different components of noise in a detector. And this is done via a log-log plot of the signal versus noise. It's also used to calculate the electron ADU conversion gain that is used to kind of translate from ADUs back into the electron units that are used to compare between detectors. So there are three components of noise. The first one is the read noise, which, as I mentioned, forms the floor of your noise signals. So you will always have a noise higher than the read noise. The second is the shot noise, which is just the straight line that goes across. And this is a Poisson distributed noise in the arrival of incident photons. So this is unavoidable. It's always going to be there for every detector. And the last one is the fixed pattern noise, or FPN, which you'll notice is present in the smaller plot from the reference paper, but not in the plot that I made for the Hamamatsu camera. These are caused by manufacturing imperfections in pixel sensitivity and signal amplification. Yeah, Shuman?
Do you know why is there a drop off at the end of the?
Oh, right here?
Yeah, for both actually.
Yeah, it's because it's the same with the linearity plot. It's kind of, it connects.
Oh, it's
So,
like the saturation point?
Yeah, so once your detector hits the saturation point, it's gonna be like completely saturated in all of the images. So when you like try to take a standard deviation of its signal across images, it's gonna, the noise, which is the standard deviation, is gonna fall off because they're like completely full, so there's not much difference in the pixel values.
So would you attribute the drop off to something physical, or is it just like some? It's just because you sorry, let me rephrase that. Would you attribute the drop off to not a reduction in noise to signal ratio, but rather something more mathematical?
Well, the drop off is just due to the fact that you've reached saturation. So if your bucket is completely full, there's not going to be much difference in the amount of water in two full buckets. That's basically just it. Because the noise here is like the standard deviation in the signal of each pixel across like 100 images. So if each of your pixel is saturated in all 100 images, you're not really going to have much noise measurements there. Right. So historically, CMOS detectors have had very high levels of FPN, which just reiterating is caused by manufacturing imperfections and result in differences in pixel sensitivity and signal amplification. So having a low FPN is very important for CMOS to kind of take over CCDs in astronomy. And yeah, interestingly, unlike the reference paper, I didn't see any FPN in any of my data, which could mean one of two things. The first one being that all of the detectors we tested were really, really good. And the second being that I went wrong somewhere. So again, since we're acquiring the camera that the reference paper used, I'll be able to verify if the problem is with me or if the detectors are good. Yeah.
Did you show a plot of FEN with CCD?
No, I don't have that plot, but we're also trying to acquire one of the CCD cameras used in the Dragonfly array from Professor Bob. So once we have that, I'll run all of these tests on that as well and get like the same characterization.
So in the right graph, the FPN, where is it? Just not
Well,
there?
yeah, it's so low, like it's minus 5.2 times 10 to the minus 5%. So it just doesn't show up in the graph at all.
Oh, okay.
So essentially what then happens is your noise is dominated by the read noise in the low signal regime.
Right.
And dominated by the shot noise, which you're never gonna get rid of in like the higher signal regime.
What is the shot noise?
The shot noise, it's the Poisson distribution, distributed noise in incoming photons. Yeah. Hmm.
No, if the angles go down, also CMOS detector.
No, these are both CCD detectors. Sorry, CMOS detectors that I tested.
And I think you said that the Hamamatsu one is the best after
Mhm.
like the linearity source.
Yeah. So. Oh, well, yeah, the Andersona, it was a 12-bit detector, while the Hamamatsu and all the other detectors were 16-bit. So this is not really a fair comparison, but it's also, if you look at this plot, what we're looking for is the fact that the dark current is over an order of magnitude lower than all of the other cameras. And like the linearity, it's not, if you have 99.5% versus 99.7%, it's not like too much of a difference. And even the read noise of the Hamamatsu is like an order of magnitude smaller, which is why it was the best one. So to end off, here are the results of the testings I did in the summer. I have run more tests since then, but I didn't have time to update this presentation since I finished it at 4 a.m. last night. But so all of the green boxes are the measurements from my tests that outperform the manufacturer reported values. The yellow boxes are ones that are kind of similar or within like the reported range. And the red values are ones that are just really bad. So as you can see with the Hamamatsu, it did outperform what was expected with the dark current and read noise and had the same gain as reported. And you'll also see with the Hamamatsu, there's something called the photon counting mode, which has 0 read noise. And that's just because it's able to, it has some internal algorithms that calculates the number of photons landing on each pixel. So instead of electrons, you're reading photons, which is why you won't really have any read noise. And yeah, there's this camera. It looks like it was the worst performing, but it was also like, I think the first or second camera that I characterized. And I only had it for about 2 weeks. So I didn't really have all of the testing and all the processes down at that point yet, which is why it might not be super accurate. Okay, and that's the end. Any questions? Yeah.
What linearity, what can we get in a algorithm?
We can use an algorithm, but I do have an answer for that. I'll have to look it up and get back to you later. I do know the answer. It's just buried somewhere in text messages with my supervisor. Okay, any other questions? Yeah.
So for like figuring out this, like the salt and pepper thing, for example, how do you actually, like, what kind of tests do you run? Do you just blast it like a constant amount of light over some period of time and then look at each pixel?
No, so for the salt and pepper identification, I believe I used the same data as I did for the read noise, which is essentially I put the lid on the camera I leave it in a dark room and I set it to take 1,000 images at the lowest possible exposure setting the camera will allow me to. And then I look at the median and the standard deviation in the value of each pixel across those 1,000 images. And then I had like some algorithm set up where if a particular pixel was like 2 or 3 sigma away from the median in at least 20 images, then it was flagged. It turns out I wasn't able to develop like a proper algorithm to differentiate between high salt and pepper very accurately. So I kind of just resorted to normal and faulty pixels. Yeah.
How do you like differentiate between the text and the camera itself and making the optics that you're using with it?
Sorry, can you repeat that?
You know, if you have like a lens on it or some sort of optic setup
Mhm.
with the camera, how do you differentiate between having issues with the sensor and having issues with the optic?
That's a good question. Well, so all of these tests that I run, they are without any lenses. So I'm able to characterize what is essentially the performance of the camera itself. And then later when we put it onto a telescope, actually, yeah, we're hoping to put it onto the telescope on top of MP in like the coming month, if weather is good. But yeah, so since we have the data and characterization of what just the performance of the camera is like, when we put it onto a telescope and we take like the calibration data on the telescope, we'll be able to identify like what is because of like the lenses and the telescopes we use. Yeah.
You say you have the CMOS to test on side factors. How do you find the deviation towards different pixels? Because I imagine the difference that you have to be zero. So let's say if it was close to zero, you have a minus difference, right? So how do you detect?
So for salt and pepper pixel testing, I'm not calculating the standard deviation between all of the pixels in the detector. Instead, what I'm doing is I'm looking at the standard deviation in the value of each individual pixel, but across 1,000 images. So it's the same as like suppose I only had 1 pixel, then that was all I had, and I just take 1,000 images on that 1 pixel, and since they're all at like the same conditions, I just take the standard deviation of the value of, or the signal of that 1 pixel in those 1,000 images. So I'm not comparing between pixels, I'm just comparing the same pixel with itself. Yeah.
How complicated is it to replace CCD with a CMOS? Like, is it something that would have to be like, if, for example, there is a decision and people are like, okay, so CMOS are actually better. Is it something that will have to implement in new telescopes, or can they go back to already existing telescopes and just like pull out the core and place it to existing?
Not sure. I think that might depend on how the telescope is made. Because if your telescope is it's of a kind where like the camera is externally mounted or something, then yeah, it should just be as easy as swapping it out and putting in the new one. Because even with the CMOS, we still take images stored as FITS files, which if you're not an astronomy student, FITS is like the data type that we store images as in astronomy. So there's no difference in that, no real difference in like the pipeline for data analysis. But if like your camera is inbuilt to the telescope to the point where you'd need to disassemble the telescope to change the camera, then I probably not worth it. Yeah. Yeah. But it's also like if you already have a working telescope with a CCD, then unless it's like a really old CCD, there's no real point in changing it to a CMOS. It's probably just better to build new telescopes with the CMOS. Yeah. Right.
So, I guess my question is, in terms of the history of the development of CMOS versus CCD, you said that originally CMOS was very non-linear with exposure, but now you're getting fairly good linearity results. So is that more of a found better materials to use in it, or we've like found some kind of way to design it better in such a way that we get higher linearity.
I don't know the exact answer, but I'm gonna assume it's like a combination of both. Like it's the same with technology, just evolving, getting better.
Do you have any questions on Zoom?
Oh, I didn't even know we had people on Zoom.
I don't think we have any. questions
Yeah.
on-
How far away is the technology from consumer?
What do you mean?
See this in our.
Oh, no, this is already used in smartphones. So your phone, your professional cameras, all of them already use CMOS, which is why, because of like the large consumer market for CMOS, like that's why the manufacturers put more focus into CMOS R&D in production. So yeah, if it weren't for consumer products, it'd probably still be like developing and using CCDs. Yeah.
Why is linearity better? Like just linear, even if it's not linear, could be not modular.
Yeah, so linearity is important because it's like if you have two stars and one of them is twice as bright as the other, when you're looking at the data and you're trying to like standardize things, you want the data to show that the star is twice as bright as like the other star. As for why we care about it being linear and not just modeling it to account for it, is like I told someone, I have the answer, I just have to dig it out from my conversation history.
Yeah, because like if you know it's like what that.
Yeah.
Probably also if you material has some wear over time, and if it's something nonlinear, it would be unclear how it would just change over time, just with the material degrading sometimes. Maybe.
Also, the analog to digital converter, it probably has like some kind of imaging resolution. So if, let's say it's quadratic in a lower regime, tiny amount, like the same amount of change in electron flux or photon flux is going to cover less of the sampling area.
All right, I think we're going to end it on this note. Once again, another round of applause for. We will be posting the recording of this on our YouTube channel, which hopefully you've already subscribed to. Yes, follow us on Instagram at PhySU. Join our Discord, the link to which you can find on physu.org. Thank you all for coming, and please watch out for the next colloquium that we'll have in the series, hopefully soon. Thank you.
Okay, really quickly, I found the answer to the linearity question. So it's basically that if you're doing ultra precise photometry, you don't want to introduce more uncertainty into your measurement as a result of like having to implement a response curve. So it's just fundamentally better to have a highly linear detector than a detector whose deviation from a linear response needs correcting.
Plus, like if you have like some uncertainty and you exponentiate it. Okay, stop.
That was actually well